Hello friends, myself Dr. Iqbal Singh. I'm going to present you the work that I have done in the last 5 years for teaching physics concept through Excel spreadsheets. Uh, Before I'm going to discuss my work, let's have some look on to about my institution, about my work that I have done. So this is the picture of my institution, which was having a great history of more than 125 years. It has been established in 1892. About my educational and professional qualification, I have joined this institution, Khalsa College, Amritsar, in 2004 as an assistant professor. Now I am working in the same department at the position of associate professor, and my field of specializations are material science, particularly the gas sensors. This is the topic of my PhD work, and beside this, I have a specialization in microelectronics and nuclear theory. Now, we know that experimental learning through simulations, uh, it has been done to enhance the conceptual understanding of the students. And we found that this type of learning encourages and promotes the critical thinking abilities in the students. And the students involved in such activities, we found that they have a greater understanding of their subject matter than the students who have attended only the special traditional lecture classes on. So simulations helps to understand some enhance the conceptual understanding of the subjects. So before we are going to start with any simulation, we have to divide it into the number of parts. First, we have to prepare the simulations and we have to select one problem. We have to prepare the simulation. And the next part is after preparation, we need a active student participation to check the success of these simulations. For that, we have to provide sufficient time to the students so that they can tell us what are the positive and negative points, what are the shortcomings in our presentation. So I have chosen deliberately a low-tech simulation method, which is the Microsoft Excel spreadsheet, as this tool has number of inbuilt commands that we can use without knowing any traditional programming language. So some of the examples that I have discussed or I have compiled in this presentation that I have compiled using the simulating an Excel spreadsheet. They are having Fourier series expansion of some periodic signals. Then we understand the diffraction of waves. Then next one is a charged particle in an electromagnetic field. We can derive its generalized trajectories. Next one is the coupled oscillators. We can add the number of factors in and the analysis of coupled oscillator. Next one is polarization. Beside the Excel spreadsheet, we also have digital storage oscilloscope applications. And for that, we can understand two new ways to learn our own experiments. One is the induced EMF, and next one is the capacitor combinations. All these problems that I have listed they are already published in international journals of physics education of IOP as well as European Journal of Physics, and I am going to discuss all these problems one by one. First problem I had taken is the teaching graphical simulation of Fourier series expansion of some periodic waves using the spreadsheets. So main highlights in this problem is student can learn how the partial sum of waves actually will help to generate the original signal. In this, we are not going into the mathematical details, but we are going to discuss how a typical signal is created using the Fourier series components. For that, we have taken the example of square wave, sawtooth wave, half wave rectifier, full wave rectifier signals. Now we have the basics of Fourier series. We know that any function is said to be a periodic one if it satisfies some condition or repeated after regular intervals of time. We can break up this function into its individual components using the Fourier series. So where a naught, an and bn, these are termed as Fourier coefficients, and they can be evaluated using these mathematical formulas. We are not going to discuss the mathematical parts. We are going to discuss how we can compile this Fourier series expansion in terms of Excel spreadsheets. So first example, we take the square wave function. A square wave function which is to be defined over the interval 0 to 2 pi is defined as like this. It takes a value 1 when x lies between 0 to pi, minus 1 when x lies between pi to 2 pi. So we can do the mathematical analysis and we can find out its Fourier series expansion is given by this last expression. Now how we can compile this into the Excel spreadsheet? So we have to organize our Excel spreadsheet, which is a cell-based structure. It is used to analyze the data and to compute some results. So we are having number of rows and number of columns. So we have to organize our work in these columns and rows. For example, in this spreadsheet, we have organized this for eighth column to include the value of x at the regular steps. Then in the column B we write x in terms of pi. In the column C we define the function which take the value 1 for 0 to pi, and then after pi to 2 pi it will take the value minus 1. Then these column D, E, F, G, they are used to calculate the Fourier coefficient at each x value. So these are termed as A1, B1, A2, B2, A3, B3, A4, B4 up to A9, A10 and B10. In the next spreadsheet, we are going to find out the coefficient. This is for number of waves, first term, second term up to the 10. Then we can sum up these coefficients for the 10 one, an and bn. These are the sum of all these one. Now we are going to calculate the partial sum of these 10 waves. So we constitute the wave 1, wave 2, wave 3 using these Fourier coefficients an and bn. If you have taken only the one wave, so this is for this one. If you compound the two waves, we consider the terms up to n is equal to 2 in the Fourier series, that will generate wave 2. If and 3, we get the sum of 3 waves. Then we start plotting these one by one waves and we check how it give rise to our final signals. When n is 2, we found that signal is almost a sinusoidal wave. It does not replicate your square wave function. But when you increase the sum of n is equal to 4 number of waves are combined together, we start getting a hump in the signal and it start approaching the square wave. Then you increase the sum to 6 terms, we are getting more number of terms. When you get the 8, we are getting again. After 10 terms, we will find it almost resembles with our square wave function. Similar examples we can take up for the sawtooth wave function, but here we have to check how much waves we have to include to generate a given signal in terms of its partial waves. So here we find in the sawtooth wave, we have to compound almost 30 waves to generate the final sawtooth signal. Similarly, we have analyzed the half wave rectifier output. You just organize your Excel spreadsheet and we find sum of 10 waves will generate almost your half wave rectifier output. In the next one, that is a full wave rectifier output. This is your original signal, but as you increase the number of partial sum in the waves of 2, 4, 6, 8 and 10 waves, we will find this convex part, it almost start touching your x-axis and you will get almost full wave rectifier output in one single you can say cycle. The next problem I am going to discuss is the simulating Fraunhofer diffraction of waves using the Excel spreadsheet. The main highlight in this paper is to find out we can teach the or student will be able to learn how a single slit diffraction pattern gets, then double slit, triple slit. You can immediately check what happens and how many secondary minimas, how many maximas are there, what we find in or learned in theory that we actually observe experiment. So Fraunhofer diffraction of slits in the N waves, the intensity at any point at an angle of theta is given by these two terms. This is the peak intensity that we can decide it by ourselves, or you can select any value. The first term is your diffraction term and second is your interference term, where delta is the half phase difference between the first and the last wave from the two ends of the single slit, and this is for the successive slits. So net diffraction pattern is to be the superposition of diffraction and interference term, and this is actually the modifying you can say fringe pattern. We can get the maxima and minima accordingly to get the conditions at any point. Let us start organizing our Excel spreadsheet for that. For this, we write down the column A in terms of theta, which you write down in terms of degree. Then you convert it the theta in terms of radian. You calculate the delta phase shift. Using this, you can use the Excel commands to calculate out the diffraction term, that is sine delta by delta whole square. Then you calculate out the phase capital delta from the successive slits, and you compute the term sine and delta and n sine delta to compute the interference term. Then you calculate out the net intensity, which is to be multiplied of your column D value with the column H value. You can simply use the formula. These are some of the parameters that we have to put ourselves, or you can say these are the parameter which we can vary, that is in the user's hand. You can take any value of the intensity I naught, you can vary the number of slits, the wavelength is in your hands, you can vary the slit width and the slit spacing, the theta values, theta initial and theta final, number of steps and step height to vary the theta value. We find that when n is 1, this is a single slit diffraction pattern. Interference term is not contributing here, that the numerator and denominator becomes almost the same and it gets cancelled out, only the diffraction term is there. But when you go for n is equal to 2, the interference and diffraction term total will generate the resulting pattern. So this is the plot of only the diffraction term for n is equal to 2, and this is a plot of interference term. But when you superimpose the two, you get the double slit diffraction pattern. You get the principal maxima surrounded by secondary maximas, and in between these we are having the minimas. And this pattern goes on repeating, although the intensity from the first envelope to second envelope drastically goes on decreasing. Similarly, you go for the three slit diffraction pattern is almost same, but we in between two maximas we get a surrounding one maxima, and you get n minus 1 minimas and n minus 2 maximas. This effect we can increase or check for n is equal to 5, n is equal to 10, n is equal to 50, and n is equal to 100. N is equal to 100 is almost just like was a diffraction pattern that we go observe on a diffraction grating. We will get the principal maxima or the central maxima surrounded by the first order, where the second order and other order intensities are almost negligible. Now in this we check the effect of wavelength on the double slit diffraction pattern. Well, let us take for example, you can compare this is the diffraction pattern for the red color and this is the diffraction pattern for the blue color. So wavelength squeeze the diffraction pattern. Then this is for the variation in the slits width, if you start decreasing the slit width, the broadness in the diffraction pattern goes on increasing. This is for n is equal to 5. Similarly, you can check the variation in the effect of your theta values. If you vary theta from -5 to 5, -50 to 50, then more and more number of fringes comes into the picture. So this is how we can vary the or analyze the diffraction pattern. Now, next one is visualizing the trajectory of a charged particle in electric and magnetic field using the Excel spreadsheet. So this paper or the article will give rise to how we can generate the generalized trajectories of a charged particle in electric field, in magnetic field, and when there is a combination of both. And we know that the charged particle moving electric and magnetic field, the force is given by the or the observed by the charged particle can be calculated using the Lorentz force. We can discuss the three cases: one, the charged particle moving in the electric field, then magnetic field, and when both are present. You organize the sheet for the t values, that is your time. You calculate out the velocity components vx, vy, vz. Then from the integration of these, we can calculate out the displacement in x, y, and z direction. These are the initial conditions, you can say. What are the accelerations, what are the velocity at the starting points, and initial and final times, what are the electric field values, what is the charge on the particle, what is the mass. All these are in your hands, you can vary. Now this is the trajectory of the charged particle. Now first case, when the particle is having experience of electric field only in the x direction, so particle is moving in the x direction only. But when you have electric field in the x and y direction, as you go for the caption B, so you start moving in xy plane. But when all the xyz fields are present, it starts moving in space. Now in all these three cases, the velocity of the charged particle at the start is 0. But when velocity is also non-zero, the particle moving in slightly a curved path. Now you organize your sheet for a particle moving in the magnetic field. You give rise to the value of your magnetic field, particle parallel velocity to the magnetic field, perpendicular velocity to the magnetic field, and you find out your x, y, z, as well as we can find out the Lissajous curve by superimposing x and y displacements. Now here we find that when particle is moving in a plane, it is just like your cyclotron motion. There is no force in the z direction. But when field is also in that direction is there, then this particle also experience a force and starts moving in that direction, and we get certain helix like pattern. You can vary the velocity, you can vary the charge, we can easily note down the effect on the trajectory of the charge particle. When both the electric and magnetic fields are there, we find that the charged particle moving in a cycloid curve. And you can easily organize your sheet and we find out the cycloid curve of the charged particle. Now next is simulating the longitudinal vibrations of a coupled oscillator using fourth order Runge-Kutta method by programming the Excel spreadsheet. Now here the generalized motion of the charged particle, which involves second order differential equation. So in order to solve the dynamics, we solve these second order differential equations using the Runge-Kutta method. So we have to analyze our problem where the masses m1 and m2, which are connected by the spring of stiffness constant S to the rigid wall with stiffness springs of stiffness constant S1 and S2. So this is your equation of motion. So you organized your worksheet for these Runge-Kutta coefficients to get the result. So we calculate out all these coefficients in this spreadsheet. The details you can find out in the paper which is presented in the European Journal of Physics. And we find out that the trajectory can be solved by taking out different cases. You can vary the stiffness among the particles. You can vary the mass particles or the initial velocities given to the charged particles. So here in the first case, you have the masses of the two particles are same. They are displaced in by the same amount. You will get the motion of the mass m1 and m2. They are harmonic motions. You add, because they are moving in phase, both the displacement are in the positive direction. So we have the normal mode x plus y. But when you go for the out of phase motion, it will go 0. Normal mode x minus 1. Both the particles are moving in xy. Lissaj's curve will be a straight line with positive slope. Here you can check out the variation in the kinetic energy and the potential energy, and we find that the energy is always conserved. Only there is a variation in the both, or transform from kinetic to potential and vice versa. So here you can check when you displace the particle in opposite direction. So these are the motion of two particles. So here x plus y and x minus y phases are taken, where x plus y goes to 0, but now x minus y will be there. The Lissaj's figure will be a straight line with negative slope. Again, energy will be conserved. Each and everything you can check. Now when particles are of same masses but they are displaced not equally, so their motion will be random, but normal modes are of sinusoidal in nature. Variation in the kinetic and potential energy will always generate the or conserve the total energy. Here the masses are of different values. They are displaced by the same amount in different directions. So again, you can check the motion of the particles. You can take the Lissaj's figure plot, variation in the how energy transform from one point to another. So number of cases we can discuss. Now masses are not of same. One is rest, another one is displaced. So all these are generalized motion of the uh, both the masses, normal modes, variation in the energy, and all that. Now next one is, then this represents the strongly coupled system. When S value, capital S value is your 10. So motion of two masses will be almost same. You can draw the normal modes, variation in energy, and Lissaj's curve easily. Then you include the damping in this one. When you include the damping, you organize your sheet, solve the Rangakuta coefficients, and you can plot. Now damping will be there. Masses follows your decaying behavior. Amplitude goes on decreasing with each oscillation. These are the plot of normal modes. Again, they are harmonic one, but their amplitude goes on decreasing. This is the Lissaj's curve. This is a strongly, you can say, system, uh, strongly, what you can say, coupled system. Then we next have the simulating the propagation of a resultant electric field vector using the 3D representation for circular, elliptical, and plane polarization waves. We can check here circular polarization, elliptical polarization, plane polarization, and we can transport or visualize its 3D picturization in using another software. We generate the data in the Excel software, and we transport it to the origin for generating its 3D picturization. So this will give rise to the picturization of your circularly polarized light. And when you transform it to the origin software, you will check it how the electric field vector oscillates in the 3D pictures or with the time. So on one axis you are having time, another you have the EX and EY, and you will get a circulating figure. For the different angles between the phase angles between X and Y, you will get the circularly polarized light, elliptically polarized light, inclined polarized light, depending upon amplitude of the fields are same or they are different. So this is your circular polarization. This is your elliptical polarization when X and Y values are not, if the fields are not same. This is about -3 to 3, or this is for -1 to 1. Uh, Now next is when you have inclined polarization, elliptical polarization. Angle is 45 or 135. Accordingly, you get the elliptical. This is for the plane polarized waves. The next problem is to how we can use the digital storage oscilloscope to learn more about the induced EMF of a magnet passing through a solenoid. This is our BSc experiment that we perform in BSc first year, and we can create a visualization to the student which create their you can say thinking ability, and actually what you can answer their various questions, and we can go directly to the experimental setup. So this is our experimental setup. This is your usual kit that we use in our BSc experiment, where the magnet oscillate between the coil. Now across the capacitor you introduce your DSO to visualize how the voltage varies across the capacitor when the solenoid moves, magnet oscillates through the capacitor. This is a single one, you can say, cycle for that. As a magnet approaches, a induced EMF goes to the maximum, then it starts reversing its direction, it starts decreasing, it crosses the center value of the solenoid, then it EMF takes its reverse sign, again it starts the decreasing part. So now here you can check when you throw it from 10 degree, 20, 30, 40 and 50. This is actually how we are changing the velocity. So when you change the velocity or throw the magnet with a high velocity, you will get more and more induced EMF that is set up. And these are the periodic curves. It oscillates from the solenoid again and again, and that curve repeats. So it also verifies your Lenge's law. Here we can check the effect of what is the output across the resistance and output across the diode that we have used in the induced EMF setup. So across the diode you are having only the one pulse. It does not mean that, but across the diode you can that one time it get forward bias, one time it gets a reverse bias. After reverse bias, and this is the voltage across the capacitor that we measure using the CRO, and this saturation part shows when the capacitor is get fully charged, and at that point your galvanometer stops oscillating. The next DSO application is visualizing the concept of charging and discharging of capacitors using the digital storage oscilloscope. Here again we have used the one experimental kit that we use for flashing and quenching experiment that we have performed in your BSc first year to students, and we can use that kit to show the capacitor combinations and how we can learn more details of this experiment using the digital storage oscilloscope. So here we have a neon bulb. We are having number of switches across the capacitors to include that into the circuit, and this is the voltage that we can vary to uh, what you can say control the flashing and quenching cycles of neon bulb. So across that you can simply connect your DSO and you check the variation in the voltage across the screen, and we find that it represents your charging and discharging cycles. Now when the capacitor gets fully charged, it go to the maximum, and here the neon bulb flashes, it discharges your circuit, and it again start at this maximum point, it again will get the flash. So flashing discharges the capacitor combinations. Now here how all these capacitors, these are connected in parallel, and capacity, more and more number capacitors you include into the circuit, so capacity goes on increasing, and it will take more and more time to what you can say charge. So this is all my work, and more number of problems I am going to you can say right now handling to what you can say, so that student can get more from these problems. So I try my best to remove the what you can say the students difficulties what they have in understanding some concepts, so they can play with these simulations and remove their uh, obstructions. So thank you very much. If you have any queries, you can mail me at this email ID. I am happy to answer your queries. Thank you very much for listening my work. and giving attention to listen my word. Thank you very much.